The examples in this second portion of the lesson really are just using all of the same skills from the first part, but are just introducing some additional complexities that you might see in the question, specifically some things that might occur in the denominator that could throw you off. So this first one, once again, is going to just involve a lot of factoring to make this easy for us to work with first. And you can see there really isn't any factoring that needs to be done in the numerators of each of these, but both of the denominators can be factored as simple trinomials. So let's see what that's going to give us. So we leave the x plus 1 on top, and this could be factored into x plus 3 and x minus 1. So again, overall, you're seeing why these factoring skills are really essential in a unit like this. The bottom can be factored into, well, x plus 5 and x minus 1 would work in this case. And now that we've got it factored as much as we possibly can, we're at a stage, at least because we can't simplify any further right now, we're now at a stage where we want to think about our LCD, our lowest common denominator. So let's think about that. Well, we know that our common denominator needs to contain every different factor that we see in each of our separate denominators. Well, we definitely see we have a factor of x plus 3, so that's got to be part of our common denominator. So x plus 3 is going to be part of it. Has to be. We also see we have a factor of x plus 5, for example. So that's got to be part of our common denominator as well, x plus 5. Because those factors already exist in each of our denominators, so they have to be part of our common denominator. But then we see that one of them has an x minus 1, and the other one also already has an x minus 1. So we can agree that definitely x minus 1 needs to be part of our common denominator, but we actually don't need two copies of it. We just need one single factor. Now maybe give myself a little bit more space here. One single factor of x minus 1 as part of our common denominator. So if there are factors that are already common to two different denominators, that factor needs to be included in your LCD, but it only needs to be included once. Now, part of the reason for that, maybe I'll use another highlighting color to help me out here, is that, for example, this original denominator can be turned into our LCD by just multiplying the top and bottom by the extra factor, x plus 5. In a similar way, this second denominator can easily be turned into our LCD by just multiplying by the extra factor, x plus 3 on top and bottom. But again, notice that we were able to turn it into our LCD even though our LCD only included one single copy of x minus 1. So we don't need to repeat the x minus 1 twice in our LCD. That's really what I'm getting at here. So let's think about how these are going to be multiplied. Well, again, if I do that little trick of just writing one great big giant common denominator, it's going to look something like this. But then on top, how are things going to change? Well, I had an x plus 1 to start with on top in my numerator, but that first rational expression, in order to get the same LCD, is going to have to be multiplied, we were saying, by x plus 5 on the bottom, but of course on the top as well to keep things equivalent. In the second piece, I already had an x plus 2, but that second rational needs to be multiplied by on top and bottom by x plus 3 in this case. So essentially, it needs to be multiplied by whatever factor was missing from its denominator. So the first one had to be multiplied by x plus 5. The second one had to be multiplied by x plus 3 for those reasons. And then we have a whole bunch of expanding and simplifying to do. So on top, that's going to become like x squared, and I'll just sort of skip a step here. Keep this in brackets for now. X squared plus 6x plus 5. And there's no real reason why I had to keep that first one in brackets, but I just did that so that it'll make a little bit more sense why I'm keeping this second one in a great big bracket. The second one would multiply out into x squared plus 5x plus 6. But I kept that second one all in one big bracket just so I can be really careful with this subtraction, because I need to expand that subtraction symbol into that entire second polynomial there. On the bottom, I still have x plus 3, x plus 5, and x minus 1. So now on top, we end up with something like that will simplify. The bottom stays the same. And the x squareds completely cancel out. We're left with just one single x and a minus 1. But then if we look carefully with what we have on the bottom, because we still have the same stuff on the bottom, this is why I wanted to carry this through to the very end. We may think that we're done at this stage, but we can actually do a final reduction at this stage. We have x minus 1 on top, and that exact same x minus 1 appears as a factor on the bottom. So because we have that entire factor available to us on the bottom, that means I can divide the top by x minus 1, which remember doesn't make it all disappear, it leaves a reduced 1 in its place. And I can divide the bottom by x minus 1, and it leaves a 1 as well. And it's really important that I left a 1 in that top spot so that it doesn't just appear as a 0. It really is 1 over the stuff that I have, which is x plus 3 and x plus 5. So it's 1 over that. That's our final result. But then I still need to state my restrictions, and my restrictions are based on anything that would have made my original common denominator equal to 0. So I did reduce away the x minus 1, but that was still part of my original common denominator, so it's going to be part of my restrictions. Well, x definitely can't equal -3 or -5. I can definitely see those from the ones that I have, but it also can't equal 1 because then x minus 1 would be equal to 0, and that can't happen. Let's do a different kind of tricky scenario that might pop up in these simplifying rationals. So now this is a very weird looking one where we've got what looks like a fraction here that's being subtracted with a fraction here, but the whole thing is really like the numerator of one great big giant fraction. So it's a very confusing looking thing. But here's how I think it's best to approach it. Let's think of this as a subtraction of rationals question on top. And we'll solve that and simplify it the exact same way we have throughout this lesson so far. And then think of this like m over 1 on the bottom, a separate rational expression that we are then going to divide by after the fact. So I'll show you how that works. First off, thinking about the top. Well, in this case, I can easily create a common denominator by just multiplying the two denominators together. So what I have from my original numerator is something that's going to have a common denominator of 4 times 4 plus m. And on the top, I'll just scroll so I can see what I already had there. I had a 1. So the first rational expression has to be multiplied by 4. So the one that I already had gets multiplied by 4. And then the one that I already had in the other spot needs to be multiplied by 4 plus m. Again, that is all sort of one big calculation that I'm going to do first. From there, then, I'm going to think of dividing the whole thing by m over 1, which may seem a bit weird, but we remember that dividing by a rational expression is really just like multiplying by the reciprocal of that rational expression. So I'm going to start to do a little bit of simplifying with all of that stuff that I have on the top there. So it's like I have 4 minus 4 plus m. Or actually, just careful there, would be actually minus m, because I need to expand that negative in. So 4 minus m. On the bottom, I still have 4 times 4 plus m. That was the common denominator I got from all that stuff on the top. And once I've simplified this down as much as possible, I'm really just going to be dividing it by m over 1. So using that old-fashioned division symbol is a nice way to help. This first piece, I really have negative m over 4 times 4 plus m. And then I'm really multiplying by 1 over m. And remember that before I actually do any multiplication, I can always look at what I have overall and see if I can reduce before I start sticking things together or multiplying together. So for example, I can divide this top numerator by m, which leaves negative 1, and divide this by m as well, which is just going to leave a 1. So this would be a little bit simpler in my final answer, and I would have just negative 1 over 4 times 4 plus m as my denominator. And now, in this case, my restrictions are based on my value of m. What can m not equal? Well, m is something that I divide by in this case, first of all. So m itself cannot equal 0 because m is something that I'm dividing by. But also, we also have this as part of a denominator, which means that that can't equal 0, or in other words, that negative 4 could not be our m value either. So as long as m is not equal to 0 or negative 4, we still have a rational expression that works. I'm going to do one final one with you that I'll mostly get you started off on, and then let you try and finish it off with some of the additional expanding and simplifying. This is one great big example that looks a little bit complicated at first, but one thing that we actually have to identify before we go any further with this is order of operations. So we see that there's subtraction happening here, but then we later see that there's division happening. So most importantly, it's the division that has to happen first. So this division takes precedence, which means we need to do all of the work with this stuff first. We need to divide those two rational expressions and ideally come up with the simplest result possible from that, and then take our result and subtract it with the first expression. So if that really requires us to do a division first, let's rewrite this so we can make it into, first of all, a whole bunch of factors wherever we see them, but also change this into more of a multiplication statement. So in this step, with this first term, I'm not going to do any calculations with it, but I will put it into a factored form. So its denominator could be like x plus 5 and times an x plus 2. That one factors pretty simply. Then I'm going to subtract, well, again, something that has a numerator and a denominator in its factored form. So x plus 4 and x minus 3 would work for the top. And on the bottom, something like x minus 6 and x plus 4, again, would work. And now, instead of dividing that, what I'm going to do is think of multiplying it by a reciprocal of that fraction. So the x squared minus 8x plus 12 that was on the bottom, I'm going to rewrite its factored form on top now. So that would be like x minus 6 and x minus 2. So again, that's the factored form of what was originally on the bottom. So that's the factored form of this expression, which is now on the top when I multiply by the reciprocal. And now what was on the top is now factored on the bottom, which could be like x plus 5 multiplied by x minus 3. Now, before we go any further, we can do a whole bunch of reducing. So for example, I see an x plus 4 here, so I can reduce that to a 1 as long as I do the same on the bottom here. I see an x minus 6 can be reduced to a 1 as long as I do the same over here. X minus 3, and here as well. And what does that leave me with? Well, it leaves me with an x minus 2 on top of one of them and an x plus 5 on the bottom. So it's actually as simple as that in my final form. So I still need to rewrite the one that I already had. That's the one that's going to start off my subtraction statement. And now I'm just subtracting a much simpler rational expression. So as tricky as these skills can be at times, hopefully now you're seeing how incredibly useful and important they can be in taking something that starts as really complex, like this original big giant thing we started with, and simplifying it down into something much more manageable like this. But we still have some subtraction to do. which means we need to find an LCD, a lowest common denominator. Well, once again, we have this situation happening where they each already have a factor in common. This one has an x plus 5, and this one's entire denominator is x plus 5, which means if this one could just be multiplied by an extra factor of x plus 2, then we would have our common denominator. So our LCD in this case must definitely include the x plus 5 factor, but it also has to include an x plus 2 factor, which means the first expression does not need to be multiplied by anything at all, or you can think of it as being multiplied by 1 on top and bottom, but the second one will. So overall, this thing is going to have a common denominator of x plus 5 over multiplied by x plus 2. And we're going to have something like 21 subtract the x minus 2 that was already there, multiplied by an extra factor of x plus 2 that we're multiplying by on top and bottom of that second expression. This is where I'm going to leave you to once again do a little bit of expanding and simplifying to see if you can get it down to its simplest form, and then use all of the different factors that we had involved along the way, particularly any ones that ended up either being divided by or in the denominator of anything, and use that to come up with your final restrictions. As usual, make sure that you check your results with the full version of the lesson, and then ask questions if you have them, and make sure that you try as much practice of this stuff as possible.